What if there were devices that could solve problems in the blink of an eye? Problems that even the fastest supercomputers would need billions of years to crack. What if we had computers so powerful that they could simulate all the processes of nature, providing us with answers to humanity's biggest questions, from the origins of the universe to the emergence of life? If so, we would have entered the thrilling world of quantum computers. Indeed, scientists at the renowned University of Oxford have recently achieved a groundbreaking milestone in this field by connecting two quantum computers for the first time, enabling them to solve a highly complex quantum task together. In this process, a quantum logic gate was teleported over a distance of 2 meters. But how does this work? Why are quantum computers suspected of radically changing the future of everyday life? And what gives them their unparalleled computing power? A recent announcement has turned heads. A few weeks ago, Google Quantum AI revealed that their quantum processor, Willow, solved a problem in just 5 minutes, a task that the world's fastest supercomputer would need a staggering 10 quadrillion years to complete. That's a 1 followed by 25 zeros. But how is it that quantum computers can make even the most powerful supercomputers of our time seem like snails? To understand this, we first need to grasp how our current everyday devices work. Whether you're watching this video on your laptop, phone, or tablet, all these devices operate using bits, units of information that can only be in a state of 1 or 0. These states are represented in today's processes by electrical currents, current on for 1 and current off for 0. Quantum computers, on the other hand, use quantum bits, or qubits. These can also be in a state of 1 or 0, but they possess an extraordinary ability that sets them apart from classical bits. A qubit can exist simultaneously in both states, or theoretically, in an infinite number of states in between. To visualize this, imagine a classical bit as a coin showing either heads or tails. A qubit, however, is like a coin spinning rapidly in the air. We can't say which side is up because it exists in both states at once. This unique property makes quantum computers exponentially more efficient than traditional computers, as they require far fewer qubits than classical bits for the same calculations. While 2 classical bits can only represent 1 number at a time, a qubit can represent an infinite number of states simultaneously. Even if we consider just 2 states, each additional qubit doubles the number of simultaneously representable states exponentially. For example, 3 qubits can represent 8 states at once, while 300 qubits can represent 2 to the power of 300 states, a number larger than the total number of particles in the universe. But that's not all. Qubits in a quantum computer can also be quantum entangled, meaning they are interconnected. When one qubit is changed, the state of its entangled partner changes instantaneously, even faster than the speed of light. This allows quantum computers to perform calculations at incredible speeds. But what practical applications does this have? At the moment, none, yet. Once the technology matures, scientists aim to use quantum computing to simulate molecular interactions and their possible states, leading to breakthroughs in drug development. Artificial intelligence could also take a giant leap forward with the help of quantum computers. Additionally, the development of new materials and the fight against climate change could benefit from this futuristic technology. However, we still can't fully predict all the potential applications of quantum computers. Some experts even believe that these machines could simulate all natural processes, unlocking the universe's greatest mysteries and answering questions about the origin of life. Why do qubits pose challenges for researchers? How are qubits even created? To generate qubits, experts have several methods at their disposal. Google, for instance, uses special quantum chips with weak currents flowing in tiny loops. Each loop represents a qubit, which can be manipulated and read using microwave radiation. The Willow quantum processor, for example, is equipped with 105 superconducting qubits. Alternatively, qubits can be created by trapping ions in magnetic and electric fields. Once trapped, these ions can also be manipulated with microwave radiation to encode information. However, the field of quantum computing still faces significant challenges. For instance, qubits must be cooled to near absolute zero, minus 273.15 degrees Celsius, to stabilize them. Additionally, qubits are extremely sensitive, and even the slightest disturbance can destroy their quantum state. Despite efforts to shield them from vibrations, magnetic fields, and other external influences, qubits remain stable for only fractions of a second. Calculations must be completed within this narrow time frame, requiring researchers to constantly increase the number of qubits working together. While quantum computers with 1,000 qubits already exist, experts believe future quantum computers will need millions of qubits to be truly practical. However, the more qubits a quantum computer has, the more unstable and error-prone it becomes, necessitating complex error correction methods. For example, the Willow processor uses a surface code, where quantum information is distributed across multiple physical qubits to form a logical qubit, preserving the necessary information even if one physical qubit fails. Interestingly, the scaling problem might be circumvented using teleportation. Scientists at Oxford recently demonstrated how to teleport a quantum operation. To clarify, quantum teleportation differs from the sci-fi concept of teleporting matter. Instead, it involves transferring quantum information, such as the spin state of an atom, to a distant second atom. The Oxford team used modular quantum computers, where each module contains a small number of qubits connected via classical and quantum channels. This setup allows the modules to remain relatively stable while collectively executing larger quantum algorithms. In their experiment, the researchers successfully coupled qubit modules to solve a quantum algorithm across modules. Each module consisted of two qubits, a calcium ion acting as a circuit qubit and a strontium ion serving as a network qubit. The network qubits were entangled via a fiber optic connection, and the collective calculations began by entangling the network qubits. Photons, coupled with the qubits, facilitated this entanglement. Once entangled, each module generated a controlled CZ, quantum gate between its network and circuit qubits. This gate inverts the sign of the digital 1 while leaving the 0 unchanged. The trick here is that the entanglement of the modules causes the quantum gate to be teleported, meaning the qubits in both modules operate within the same gate. This allowed the Oxford researchers to combine the separate quantum processes into a single, fully interconnected quantum computer. To prove that the modules were truly computing together, the team had their modular computer execute the Grover algorithm, which searches for a specific entry in an unsorted database. The collective computer solved this task flawlessly. While previous experiments had exchanged quantum states between physically separated systems, this was the first time an algorithm was executed by a distributed quantum computer, demonstrating real interaction between the separate modules. According to the scientists, this achievement could lay the groundwork for a future of more powerful and scalable quantum computers, as well as the foundation for a quantum internet. And now, with just one click, you can lay the foundation for your future subscription. Feel free to hit the like button and subscribe so you never miss another video from us. See you soon.